Welcome back, everyone. Really good to see everyone after the spring break, and hopefully everybody had a good break. So now we are in the last stretch of this course. So yeah, I was just checking if the recording was on or not. So we are in the last stretch of the course, and we were midway, somewhere midway, while discussing about transformers. So what we'll do today is finish up transformers and leave part of it of that slide deck and move on to a next sequence of topics, which is related to online learning and reinforcement learning. And that's going to capture some ideas about how prediction blends into decision making and and so that's what we'll try to do in the next 3 weeks. And I'll also motivate a few more logistical things. So let me actually quickly open up the chat window so that I don't miss any questions. Uh, okay. So I hope everybody is able to hear me right. Uh, okay. So um, in terms of logistics, where are we? So we are um, going to talk about, as I said, we're going to talk about decision making from today and for the next roughly next couple of lectures and maybe spill over to the one more lecture. So today we're going to talk about something called multi-armed bandits, but don't worry about it. We're going to talk about it at length. And next time we're going to introduce what is called reinforcement learning. So and then we'll continue on the same topic the week after that. And hopefully come back to some deep learning topics which are not concerned with decision making in potentially one of the lectures towards the end of this month. Okay, so the reason why I'm kind of stopping at transformers and not talking about more variations of transformer architectures, and we'll talk about transformers again today, is that we have assignment number 4, which is due in 3 weeks. And we also have the project deliverable, which is due in 4 weeks from today. So keeping in mind that, I guess those deadlines, assignment 4 primarily is about decision making. It's actually assignment 3 was the hardest. So you guys have gone through that in the past couple of weeks. So assignment 4 is going to be a little bit easier, but it's going to focus on decision making, and in particular some reinforcement learning ideas. And we're also going to blend some aspects that are new, which are going to cover in the next 2-3 weeks, and also some aspects which are old, like a neural network and PyTorch and so on. Okay. So with that in mind, um, yeah. So in general, I would say April 20th. So it's the beginning of April now. So April 20th, which is about 3 weeks, is assignment 4 is due, either on the 20th or the 19th, I guess. And and the week after that is the project deadline. Keep, as usual, with respect to projects, try to pace yourself properly. You have a project plan, right? So everybody has a project plan. So if you're hitting any, I guess, issues, contact Teng or me via email, and we'll see what we can do with helping you out. Okay. And with respect to, so there's going to be project presentations on April 28th. And the time slots for the presentations I've already entered in that shared Google Sheet. So let me just share that link again here. Yeah, as you can see from the sheet, there's about 10 different presentations. So which kind of implies that there's not much time for each team. So but that's fine. I think it'll be good to showcase the interesting stuff that you've done beyond what we've already covered in the lectures. So you don't have to talk about things that we have already seen in the lectures, but the new things that you have tried out or discovered or experienced with when working on your project titles, project topics, you can talk about them. Okay, so yeah. So and as I said, what I'm going to do is directly, we're going to start talking about transformers again today. We'll just finish up the description of the transformer architecture, both the encoder and the decoder side. And then I'm going to come back to lecture goals and so on, because we're going to start a fresh set of topics about decision making, or in general, I guess a specific type of decision making called online learning and reinforcement learning. And so I'll bring back lecture goals and so on at that point. Okay. Let me share my slide deck. Yeah. So I hope everybody can see my slides. If you cannot, just let me know somehow. Again, the chat window. Okay, so thanks. Somehow when I share the screen, the chat window disappears. I need to figure it out where it is. Okay. Good. Okay, so last time we spent a lot of time revisiting attention, and we wanted to do that because anyway it was something that you would have seen if you use the second question in assignment 3. It involved a particular decoder which had attention in it. That's right. So we did talk about this encoder decoder attention, or attention mechanism specific to LSTM or RNN based models, right? Where you keep track of all the hidden vectors and somehow selectively take an weighted average of them, and that vector is concatenated with your state while trying to predict each word and things like that.
Hi.
Okay. Yeah. Yes. Somebody had a question? Well, okay, I don't think anybody had a question there. Okay, so that's what we were talking about. So that was Steph. That was. I'm just recapping things that we've covered before, just so that everybody can refresh what we did. So this attention and sequence models, since you have spent a lot of time on assignment 3, question 2, you might be mostly familiar with it by now. So this is about encoder decoder attention, and you'll see it's actually reused in the transformer architecture. So we'll get back to that, but I'm not going to do a recap of that. And what we'll jump back, what we'll get to directly is we'll focus on the transformer architecture. Okay, it's a name. Okay, it's a name for a new class of, I guess, neural networks. The way the layers are stacked with respect to each other to achieve some prediction goals. And in particular, we are talking about capturing sequential relationships, and if you recall from last time, we were talking about a neural machine translation. So we'll again go back to language to language translation application as the running example. But we'll kind of get ourselves familiarized with the transformer architecture. We have already started doing that. Last time we actually saw self-attention and multi-headed attention. I'm going to fill up a couple of additional things that completely describe the encoder, and then we'll also look at the decoder and just wrap up with training. So what we'll not do is the next couple of topics listed here in the slide deck, which is how do you use such a, let's say, a transformer based model. Let's say you already have the weights. How can you use that in place of, let's say, Word2Vec or Glow? I mean, you have used Glow in the assignment before, in the third assignment, but how do you use, let's say, a transformer based model weights? And now these are not these embeddings themselves. Okay, these are model weights from which you can of course generate essentially embeddings for words, and those are called contextual embeddings. But we'll not look at that right at this session. We'll come back to this after we cover decision making, online learning and reinforcement learning first, because that's, I think, you need suitable time for the assignment number 4. Okay, so we'll come back to this towards the end of the one of the lectures right after we finish online learning. So we'll come back. So what we're doing now for the next, I guess, half an hour or so is really wrap up transformer architecture. So some of you remember it, some of you don't. If you don't, let me recap the details. Some details I'll be a little bit quicker because we have already seen the notion of self-attention, but definitely do stop me and ask questions if you don't recollect, or if you have if you're unclear on something. Okay, so actually, so the running example, as I said, is language translation. So we have a sentence in French, and we want to translate into English, let's say. And you could have your model that you really worked on in assignment 3 as the intermediate object, right? Instead of that, we will look at a new architecture. Okay. And this architecture's, I guess, main feature is the notion of attention. Okay. And attention, is a generic word. It means a lot of things outside this, this particular technical field. But here we mean something specific in terms of in terms of how hidden vectors and so on are operated on. Okay. So let's talk about the architecture. Attention in this case is just a nomenclature given so that we can have an interpretable understanding of how this architecture is laid out. What we'll do, and I've mentioned it a couple of times before when we're looking at other architectures, is we are just going to look at a forward pass. Okay? We are like, we're not really thinking about training, right? We are only describing the model here, which means that we are saying, hey, if an input is given, how does the input get transformed to get as the output sentence? Okay, so that's a forward pass, just like everything that you've seen with CNNs, with RNNs, and fully connected layers, and so on, right? Fully connected networks, and so on. So So transformer architecture has two parts, two, I guess, big parts. The encoders are a chunk which are related to what are called encoders, and a collection of decoders. Okay, it's in plural. And if you open up this collection on the left side, you will see a bunch of boxes in green. So let me actually open it a little bit. Yeah, bunch of boxes in green. So these are a collection of encoders, and on the right side is a collection of decoders. Okay, and the number of encoders and the number of decoders is something that you choose a priori, and it's not related to the sentence length in your corpus. Okay, so this is in this example, we have 6 encoders and 6 decoders. They have nothing to do with the sentence length. So whether the sentence length is 3 in this example, or 2 that we'll see later, or if it's length 20, um, it has some impact on things that we choose inside an encoder, but it doesn't have an impact on number of encoders. Okay, in that sense, whatever you learned with respect to RNN units is not related to what we're doing here. Okay, so if you thought of RNN units, there'll be a number of RNN computation steps. They are not related to the number of encoders here. Okay. So as you can also see from this diagram, the sentence is actually inputted all at the same time. So all the words are given as input to the computation, whatever computational blocks are there at the same time. So all the 3 words are passed to the first encoder block at the same time, and some 3 other quantities. So clearly 1 quantity per word is also passed to the next encoder, and similarly 3 quantities are passed to the next encoder, and so on. Okay, so it's basically 3 quantities because there are 3 words. If there were 20 words, there'll be 20 quantities. When I say quantities, I think of them as vectors, basically. They're getting passed over and over again. Okay. And this attention mechanism is going to be something which is going to be inside the screen block, and that's what we're going to describe next. Okay. Um, the difference between the green blocks and the decoder blocks on the right is that they're actually very similar. So actually, that's why we'll spend a bunch of time on the encoder description. Opening up the green boxes on the left side, and we'll see that the decoder is very similar to that. Okay. And we'll also talk about what is being passed from the encoders to the decoders when we get there. So um, so with that, let's get into the encoder. So encoder is actually just again, there's a layer-wise interpretable view of how we're going to describe it. So encoder is again composed of 2 sub-blocks. One is called the self-attention block, and the other one is the usual fully connected layer, essentially a feed-forward neural network. Um, and uh, and that's about it. And so there's going to be, so whatever is the input to the self-attention sub-block, again, as I said, if there are 3 inputs, there's going to be 3 outputs. If there are 5 words in the input, there's going to be 5 outputs. And generally, these outputs are going to be vectors. Okay, so that's how this block level view is. So let's now open up the. Let me quickly comment on a couple of more things. So in the decoder, you have actually the same type of a layer. Okay, so uh, if you think of, just like when you were using PyTorch or Keras, you have this blocks, right? You had nn.con2d or nn.embedding. So similarly, you would instantiate something like nn.self-attention. And so the same block would be used inside the decoder as well. So and similarly, the same type of forward of fully connected layer would be used in decoder as well, but there will be an extra layer corresponding to what is called encoder decoder attention, and this is something that we've already seen. Okay, so encoder decoder attention is about, hey, what is some weighted average of the hidden vectors corresponding to each word. So remember, if there are like 3 words, there'll be eventually three vectors here at the end of the day. After passing through multiple encoders, also you'll have something like 3 vectors. It's not exactly going to be vectors, but for now, let's just say that they're vectors. Okay, 3 things. Then encoder decoder architecture, encoder decoder attention is about trying to use some weighted average of these guys while trying to predict the next while trying to predict the output. Okay, so if it's the last decoder, while trying to predict the word, for example. Okay, so we'll get back to this, but encoder decoder attention is something that we've already seen. Okay, and this was just about some sort of getting a weighted average of hidden vectors, where 1 hidden vector per word roughly in this application. Okay, or if from other sequence applications, it will be 1 hidden vector per uh, unit of the input sequence. Okay. So anyway, so what I'm trying to say at this slide is that there is a decoder is pretty much very similar to an encoder, except there's an encoder decoder attention subblock in there. Yeah, and I guess the main point I already made, that all the words are processed at the same time, which is different from an RNN or sequence model. Okay. Um, yeah. So let me actually now describe in detail this encoder. So as I said, inside the encoder, we have to decide, make some choices. So for example, um, we need to decide, depending on the corpus, what is the longest length of the input sequence that we're willing to process. Okay, so if there are at most 20 words in all, at most 20 words in the longest sentence, okay, in your corpus, or anything that you'll see in the future as well, then the encoder will have some capacity to only process up to 20 words, like Z20. Okay, don't worry about the Z aspect. We'll talk about Z's, but you can only process at most 20 words. Okay, that's something that you need to decide beforehand. Okay, but all these 20 words will be processed at the same time. Now, second thing is, there's always going to be vector representations at various stages, and that is also something you need to decide. And that's very usual. Like in fully connected layers, you would have chosen the number of hidden layer size, or the number of hidden units. Similarly, here you need to choose some things, like for example the embedding size. Okay, here I just mentioned 512, but for example, this input, for example, it needs to be 512. Um, and similarly, all the other vectors will also be 512, and so on. Okay. I mean, this is just a choice. This is determined by the size of the matrices that are involved, and we'll actually open up this block now, and we'll see what are the matrix operations that are going on. Okay. Any questions about this point? We just went from, hey, transformer architecture is a little bit different from sequence-to-sequence models that we've seen, RNN-based models that we've seen. And we zoomed into the N encoder out of, let's say, 6 encoders. And inside each of the encoder, there are these 2 sub-blocks. We're going to zoom into one of them now. Okay. And it'll also justify why it's called self-attention, but we'll talk about that next. But any questions so far? Okay, so if the question, certainly use the chat box. Okay, so let's move into opening up the self-attention block. Okay. Um, yeah, I guess this slide is just saying that this is self-attention block. So what it does is basically some computation, and we're going to talk about that in a second. But let's say we are at the first encoder, which means that the first encoder is supposed to take, we are talking about machine translation. So the input is going to be embeddings of words. Okay. So the first encoder is going to take all the embeddings together. Let's say there are only two words in this example. If there are 10, there are 10 words, there are 10 embeddings. Let's say there are two embeddings. Self-attention somehow does some computation such that at the end of the day, you'll get an intermediate vector Z1 and an intermediate vector Z2. So one vector corresponding to each word, such that that vector is determined by, for example, both the embeddings. Okay, so both the embeddings are, in this example, both the embeddings, but in general, all the embeddings determine Z1, all the embeddings, input embeddings determine Z2, all the embeddings determine Z3, and so on. Okay, so in that sense, um, but but the word self-attention means that when I'm computing Z1, Z2, and Z3 and whatever, I'm gonna make use of again attention in some sort of like a weighted combination of if not these original embedding vectors, some transformations of them. Okay, I'm gonna do a weighted combination of some transformations of these original embedding vectors. Original, when I say original embedding vectors, is these green things at the bottom. So let's actually look at that, really what is the computation going on. So the computation is as follows. Given, so we are talking about the starting encoder, or the encoder which really takes the input sentence or input embeddings of the words. But this the same thing applies to any other encoder block, okay, any other self-attention location. So you get a bunch of, you get, in this example, you're getting two embeddings, one embedding per word. What you're going to do is for each of these inputs, okay, in this case, these are really word embeddings, but it could be something else if it's a later on encoder, if it's the sixth encoder, for example. Given those two vectors, you're just going to create three transform vectors, okay, three vectors. Okay, that's called Q1, K1, and V1, three vectors. So from the starting vector, input vector, I'm just going to create three vectors: a query vector, a key vector, and a value vector. Okay, and the names are given such that they kind of resemble what operation is going on with these vectors. Okay, remember our objective is to create eventually a Z1 vector and eventually a Z2 vector. Okay, but Z1 and Z2 vector will make all these, for example, all these six vectors here. Okay, and Z1 and Z2 also need to capture some sense of attention. Okay, so that's what we want to take away from the next this slide and the next couple of slides. So first step, from the green vector, we create three vectors. Okay, and generally this is smaller sized vectors. For example, the query vector is of dimension 64, whereas the original embedding vector could be of size 512. Okay. Um, Okay, so first step one, as I said, create these three vectors. Step two is somehow compose these vectors. Okay, and how is that? Somehow compose these vectors to get Z1, somehow compose these vectors to get Z2. Okay, so let's talk about how do we get Z1. And the idea is you pick the whatever you designated to be the query vector, the 64 dimensional one. You multiply that with both your own, you multiply that with the key vectors of every word. Okay, so key vectors for your own word, key vector for the other word. If there's one more word, key vector for that word, and so on. Okay, at that input and so on. So you multiply two vectors together. They should be the same dimension, and you get a number. Okay, so that number is some sense of how important is this word to determine Z1, and how important, similarly, here I'm not showing Z2, so let's only talk about Z1. So this score here, this multiplication, is just saying how important is this word to create a Z1 vector. Okay, not the word itself, not the green vector itself, but it's some sort of importance of that word. Okay, that location, the word at that location. So we get this course, and the next step is, so step two first get the scores with the query, multiply with every key vector. You get a bunch of scores, bunch of numbers, normalize them. Normalize just means scale them down so that they're the actual numbers between 0 and 1. Okay, and this is something that we've already seen before. You can always apply a sigmoid transformation. You can divide by the maximum value and things like that. You have seen those types of scalings. So here, in particular, this particular architecture, which was proposed in fall 2017, 4 years ago, they do a certain type of scaling. And so we are going to be faithful to that type of that variant. And of course, subsequent transformer variants have different types of choices that they make. So here first they divide by some particular number so that everything is the numbers become smaller, and then they do a softmax operation. Okay. Here, what in particular, they divide by the square root of the dimension of the query vector. So here it's divided by 8, but that's just some constant division. And then you have a bunch of numbers. You can do a softmax transformation, which is basically e to the power that number divided by e to the power all the other numbers, right? So this transformation you must have seen from session 1. So then you get 2 normalized scores. Okay. So with these 2 scores, we are almost ready to get the Z1 vector. Okay? And similarly, we'll repeat this for Z2 vector, Z3 vector, and so on. And all this can happen. There's no sequential dependency between Z1 and Z2 and all that. Okay. So once we have these scores, what we do is do a weighted average of the remaining things that we did not use. Okay. And we're just going to do a weighted average of the value vectors. So that's what it is described here. So you just multiply the score times the value vector v1, another score times value vector v2, and then add them up. Okay, and this is something that you've already seen while we were talking about attention mechanism 2 weeks ago, or 2 weeks ago. So, and that gives us the Z1 vector. Okay, so Z1 is nothing but the score 0.88 times v1 plus 0.12 times v2. And that's Z1. And similarly, you get Z2. Okay. Okay. So any questions at this point? Remember, the self-attention block has to produce, given a couple of, let's say in this example, a couple of inputs, it has to produce a couple of outputs. If there were, if the problem had like, if the instance had like 4 words, then it has to produce 4 outputs. Okay? But since we are running example as only 2 words, so this is what the self-attention part inside the encoder does. Okay, so this is a recap. So I assume the silence means that you remember this already. So okay, so the next couple of slides are just showing the same thing what we described in a more, I guess, matrix vector multiplication notation. Okay, so basically, how do we get query vectors? We can get the query vector for both the words together by just multiplying with a linear transformation matrix. Okay, so if you multiply, so let's say you had embeddings for the first word, embedding for the second word, you just stack them one below the other. So each row corresponds to a word. Then you multiply with a matrix. Okay, you multiply with this matrix, and if you choose the dimensions, so yeah, if you choose the dimensions properly, then you get the 64 dimensional 64 cross 1 dimensional query vector for each word. Okay. Similarly, you can multiply with the matrix to get the key matrix, and similarly, you can multiply with the matrix the inputs to get the values. Okay. So inputs, by the way, only make sense at the first encoder. At any other encoder, it's just going to be whatever was passed on from the previous encoder. Okay. So query vectors, key vectors, and value vectors are just generated using simple matrix transformations. And these are the things that we need to learn. So you may have a question of what are the parameters in the transformer architecture. These are, for example, some parameters, these 3. Okay, these are just one set of parameters. There's going to be more, but these are the first set of parameters. Okay. And similarly, this scoring and then getting a weighted average, which gave us z vectors, 1 per word. That whole operation is summarized into a small, compact notation this way, where you once you have the matrix, you multiply with the transpose of the other matrix. In this case, once you have the Q matrix, you multiply with the transpose of the key matrix, and and do a scaling. This is just a multiply by a small number, and take a softmax of this uh, matrix, resultant matrix, and then multiply with the P matrix. Okay, so this is just matrix multiplications going on here. But at the end of the day, this is just matrix notation to say exactly the same thing that we went through earlier. Okay, so which is whatever computation we saw here is exactly what this matrix notation is showing. Okay, so that's the computation of one computation that happens in the self-attention layer. Okay, but there's a twist to the story, is that the self-attention computation that we just saw, this actually is made many times. Okay, and that's captured in this phrase multi-headed attention. So what they do in the transformer architecture or inside the encoder or inside the self-attention module is that they don't just use the input to get one query matrix, one key matrix, and one value matrix, okay, for the bunch of words. They actually get 8 sets of them. So you get 8 sets of query matrices, 8 sets of sorry, 8 such key matrices, and 8 such value matrices, and similarly 8 such z vectors. Okay, so the z's that we see here, these are computed 8 times. Okay, not with the same parameters. So now you can imagine for each such computation, I may have potentially different parameters, right? And anyway, they will be initialized and learned, so they could be learning different parameters. Okay, so that's the idea of multi-headed attention, that you just repeat this computation 8 different times. 8 is just a choice in this original architecture. You can choose other things. And there's some rationale behind why multi-headed attention makes sense, or why computing multiple times these z's in parallel, okay, independently, makes sense. It is just to say that, hey, maybe we can capture the patterns in the data better. Okay, that's roughly, it's a hand wavy reason, or informal reason here. And people are trying to formalize this experimentally as well as theoretically, why multi-headed may make sense or may not make sense. But for us, we're studying this architecture, so let's move ahead with that. They are making this choice, okay, that they're computing multiple things in the same layer. But remember, if I had an originally a, let's say, 512 dimensional vector, and at the end of the day, z1, z2 could be 64 dimensional vector if the value vectors are 64 dimensional vectors. But if I multiply, if I compute them 8 times, I'll get a huge set, right? So I'll get z0, z1 to z7, those 8 vectors. So I need to again come back to some fixed dimension that I should pass to the next encoder, okay? Or the next, not just the next encoder, in this case, one more fully connected layer that I need to pass to. So what I'll do, what they do is go from multiple such z vectors to again a single z vector. And how do you do that? Again, you have to do some sort of linear combination, and that's achieved using another weight matrix, another matrix. So as I said, so you can, here there are only 2 rows because there are 2 words in this running example. But if there were 10 words, then there'll be 10 rows. Now we just concatenate a row with another row with another row 8 times. Okay, and that vector we somehow need to shrink to a single vector, because that's what we want to pass to the next sublayer. Okay, so to get to that sublayer, which is shown below here in this slide. So we multiply the original matrix. So multiply these z's, intermediate z's that we computed from different attention heads, into a single z vector, and that's just a linear transformation. Okay, and that's multi-headed attention. That's pretty much multi-headed attention. Now, and the same thing we are just illustrating using again a huge diagram. So basically, you have one set of input embeddings if it's the first encoder, or you'll have a bunch of some vectors if it's some, let's say, the third encoder or the fourth encoder or the sixth encoder. From these vectors, you'll do some 8 times computation to get some 8 times z vectors, 1 per word, remember, and then they'll be merged together using a linear transformation into a one into one z vector. So one z vector per word, okay, which is of the right dimensions. Okay? Otherwise, you would have 8 copies, so much longer z vector. Okay? So that's again recapped here, and this was just an illustration. There was a slight tangent that we took last time while we're trying to talk about, hey, how does multi-attention help, or in general attention help? Is that if you look at this word, this sentence here, the animal didn't cross the street because it was too tired. And there's some, they've broken them into tokens here. So if you look at the vector for, if you look at the vector for the word it, okay, the vector for word it, you have some embedding from which you're creating the z for the word it. When you computing it, okay, turns out that because of the this course, you can see that maybe one attention head might focus on giving high scores to, for example, the an animal, to show that, hey, it probably represents the animal, and maybe a different attention head could focus on the word tired to say, it has to, is somehow related to tired more than all the other words. Okay. So in some sense, attention is all about, hey, if I'm trying to get a representation for the current word or current token or current index element, then how, how is it influenced by other words? And of course, it's influenced by some other tokens or other words more than some other words. Okay. So in this case, it is influenced by, in the first, so the orange column represents one attention head and the green column represents a different attention head. And here you can see that, and the darker color of orange means that there's higher scores for those coordinates. Scores, remember, queries times keys. Similarly, there's higher scores for tired and street and was, instead of these other words that are present. Okay, so that's what's being shown in this illustration. Yeah, so that's where we stopped last time. So any questions before I move forward? So last time we just discussed about the self-attention layer inside the encoder block inside the transformer architecture. Okay, so so that's actually the key component. So if you have questions about attention in general, do ask in the channel, in the chat, or afterwards, if the class is over, if you still have some lingering questions. So what we want to do next is discuss a few more, I guess, bells and whistles that complete the encoder block. Okay, so it's not like you will actually write this from scratch. Actually, nn.transformer, I think, has a prepackaged such a block, such a computational unit already. But it's good to understand how this class of models, which has become popular with the most recent breakthroughs happening mostly on this type of architecture. It's good to know what all is going on inside at least the first model that kind of proposed this. Okay, so the first point is about encoding. So the first point is about, hey, we are processing all the words at the same time. How do I know which word is first and which word is which word is to the left and which word is to the right? Okay, in the sense that if you permute the words, it's almost as if it's the same computation. Okay, like without some extra, I guess, information, it's unclear why word to the left and word to the right, have this order relationship maintained, and how is it captured? Okay, at least from the previous description of what I've said. Okay, to fix that, you need to add what is called positional encoding. It's just a simple trick. The trick is, what you do is, before feeding, before feeding embeddings of words to the first encoder. So let's say first encoder, before feeding the green words that we saw, like thinking machine in the previous example, or this French sentence, before feeding the green vector, what we do is we add an extra vector to each of these green vectors. Okay, these green vectors themselves could be word embeddings, maybe globe embeddings, or maybe some randomly chosen embeddings, or one hot encoded embeddings, whatever they are. Okay, you will add basically an extra vector to each one of them, and only the transformed vector is what you pass as input. Okay, so it's just an input pre-processing step, but you do that at every for every example at when you pass it through the network. Okay, so what is this yellow vectors that I'm adding? Are they all the same? How do they capture position? Actually, the idea is pretty simple. So the yellow vectors are just to capture, they add some signal such that, if the yellow vector has some pattern like this, it means that this word is to the left, or is one of the first word. For example, in the example, this is the first word, and with a slightly different bunch of numbers in the yellow vector, it captures the signal that this is the second word, and if it's a slightly different vector, it captures a signal that is the third word. Okay? So this is extra information that you're somehow, like, if you could encode, hey, this word is number one, this word is number two, if this word is number three, how would you do that? There are many ways to do that. Like one way is to concatenate an extra one hot encoded vector saying that, hey, this is the first word. And then for the second word, you would have one hot encoded vector, which is saying in the second coordinate, let's say you put a one and say this is the second word and so on. So there are many ways to somehow capture the idea that this is the first word, this is the second word, this is the third word. But the way they have proposed is this way: you add an extra signal vector. Okay, so it's a addition operation. And where do we get these vectors? There are actually some design choices that they propose and subsequent papers propose. So how does it look like? These are basically what I'm trying to show in this picture is just that these vectors have some pattern if you like plot them using IM show, or if you plot the matrix, okay, matrix where each um, um, yeah, each row corresponds to this vector. Yes, so each row corresponds to um, extra signal vector they want to add. So here we are showing 20 such rows because I said maybe we only our corpus only has 20 words, so we need to decide pre-decide in the transformer architecture what is the largest length of the sentence that we're going to process. If there are only 20 words, then you only need 20 positional encoding signals. Okay, and we know that the embedding was 512 dimensions, so that's why I think this is 512 here. It's a 512 length vector. And if you just IM show, you will see that, hey, the positional signal, which signals that, hey, this is the first position, is slightly different from the vector that represents the second position, and it's definitely very different from the vector that corresponds to the 20th position. So these are just additional signals that help the architecture know that, and this is information is kind of needed for you to capture the sequential aspect, the order relationship between the words while encoding and therefore also while decoding. Okay. Yeah, sorry, I think I was showing this example for a slightly different model called transformer to transformer, but the original paper also had a very similar encoding. So um, yeah, position 0 had some pattern, position 1 has some pattern, and so on. And this is something that you add to the input. Okay. Um, yeah, in this vectors are 64 dimensional, and there are only 10 such positions being shown here. But you get the sense, right? These are just vectors that you add right before you pass the embeddings of the words into the first encoder in the transformer. Yeah. So that's positional encoding. Okay. The second idea is the idea of residual connections, and this is something that you've seen with ResNet. We talked about ResNet a couple of times, and it was also present in assignment number 2. So I will not spend too much time here. So the idea is to have skip connections or residual connections. So what you do is, so you're passing an input, right? So if you saw a previous example, there was an x1 and x2, right? X1 and x2 being passed to the self-retention block. And from there, we got Z1 and Z2, right? Inside the self-retention, we saw how to compute Z1 and Z2 with this multi-head business and all that. But what we also do is we'll take the same X1, add it to Z1, okay, and take the same X2 and add it to Z2. So basically, what we're going to do is Z1 plus X1 and Z2 plus X2. Okay, so that's the add part. Okay. We're going to add them. And so let's call it Z1 prime and Z2 prime, some newer vectors. This is a skip connection that you should be familiar with when you saw residual networks before, ResNets before. And then we'll also do something called normalization. Okay, so addition I just showed you. If Z1 is equal to so Z1 plus X1 plus Z2 plus X2, that's in the matrix form is just this. It's just two matrices. Each row corresponds to each word. So you just sum of the matrices. So you get a summed up final matrix. And then a normalization step happens, which is very similar to bash norm in the idea that, hey, bash norm helps in dealing with gradients and helps in training because the gradients are now transformed. Numbers are not blowing up or numbers are sufficiently positive, negative, and all that. Similarly here, there's this idea called layer norm that's used to, again, transform the um, uh, summed up output. So X plus Z, first sum it, and then you do a layer-wise normalization. Layer-wise normalization means something yeah, layer-wise normalization is a paper actually from 2016 by Jeff Hinton and some of the folks, and the layer-wise normalization idea is actually very straightforward. It just means what you do is you want to normalize, which just means that, hey, I have a matrix, which means I have a matrix where each row corresponds to a vector for each word. So if I have two words, there's going to be two such vectors. I need to somehow um, normalize these vectors. So what can you do? So what you're going to do is just compute the mean and variance for so here, as it says, you compute the mean and variance for all the summed inputs to the neurons in a layer on a single training case. So a single training case for us is a single sentence or these two words, which is going to um, sum up the entries of these vectors, take the mean, and also compute the variance of these entries, and then divide and then do the subtraction and division such that we get a normalized number. Um, so in contrast to bash norm, where we needed a batch, and across batch we were for the same neuron, across the batch we are computing a mean statistic and we are subtracting. For the same neuron across the batch we are computing a variance statistic and we are dividing. Okay, that's what we were doing in bash norm. Here we are not doing any mean and variance computation per neuron. We're saying, hey, all the neurons produced all these numbers, let's say 10 numbers or whatever, 512 numbers. We're just going to take average across the neurons for the same single training example, take the variance computation across all these neurons, and then do a subtraction and division using them. Okay, that's layer norm. And that's what is meant by an add and normalize step. It's not really a explicit layer, but it's something that you do. And that final output, I guess let's call it again Z1 and Z2, and that's what is passed to the next feed forward sub block inside an encoder. Okay, so the encoder has a lot of things going on. We saw attention, then we saw positional encoding. That is something only specific to the when we input let's input a sentence. Now we are seeing residual connection. Okay, so residual connections, which is skip connections, and then we're also seeing extra normalization that is happening. Okay, so it's just some sort of scaling down the numbers. You must have done a lot of normalization when you're doing even working with tabular data with scikit-learn or in R before. So it's just like that. Okay, right? For example, has nothing to do with the other examples. The normalization has nothing to do with the other examples. Next, once you get the Z1 and Z2, let's say we have, those are the extra steps that you would do. Once you get the Z1 and Z2, and these Z1 and Z2 are what is passed in this, what is passed to the next feed forward sub layer. The feed forward layer is a simple, we know what a feed forward layer is. Once you have a vector, a feed forward layer is just doing a matrix multiplication to get a output vector, right? So here, this feed forward layer will have uh, is gonna, this is basically a matrix which is gonna get multiply every word, in this case 2 words. If there were 10 words, there'll be 10 such multiplications. But they'll have the same parameter. Okay, so this is the same parameter here, and you get some output word. Again, you will do a add a normalize step, very similar to what we did here. So whatever was done here is going to be repeated here. Again, there'll be a skip connection and a layer-wise normalization. And after that, you get an output which is passed on to the next encoder if there is one available. Okay. Uh, or if not, you'll stop there and then you'll try to move on to the decoder side. Okay. So yeah. So I wanted to quickly recap the encoder. I mean, you can already see on the left side of this diagram, you kind of understand what's going on, right? So on the left side of the diagram, there are two encoders, and we've already discussed pretty much every block there, the green things, the blue blocks, the feed-forward blocks, the green blocks, and the, let's say, um, red blocks or orange blocks there. So any questions about things on the left side of this figure on the slide here? Okay, so then let's continue with the forward pass. So we have, so since we have two vectors, we get two uh, vectors as outputs. Okay, and what we'll do is pass on both these vectors to each of the decoder, but we'll pass it to the encoder decoder attention sublayer inside the decoder. So let's say there are two decoders. Then the overall architecture is that, let's say we computed two vectors here. Let's call it Z1 and Z2 again. Those two vectors are basically used for the same type of attention that you've seen for RNNs. Okay, so in RNNs, there were hidden vectors. And then somehow you would do a weighted average of them to concatenate while producing the next vector, right? So here it's the same idea in this encoder decoder layer. But in addition to that, the decoder will also have the same addition and normalization idea, which is skip connections plus layer normalization. It'll also have the self-attention idea, and it'll also have the feed-forward idea. So these are all things that we have talked about when we talked about encoders. But what's going to be different is that decoder doesn't have all the words, right? Decoder doesn't have all the words at the same time to pass forward, right? So the whole point of decoder is that it produces, one word at a time. Okay, so and that's achieved as we discuss in the next couple of slides. But let's say we computed um, yeah, let's say we computed words in this example, there are only two words. Then finally, there's going to be a linear transformation of the two vectors here, and a softmax operation to get a distribution over words from which you'll get the next word. So let's actually discuss how the decoder slightly differs from the encoder. So the outputs from the top encoder unit, there are two vectors. Let's call it Z1 and Z2, even for the last encoder. They are again transformed to keys and values. Okay, how do we get keys and values? So this time we'll not get queries. Okay, how to get keys and values? Again, some linear transformation. So the moment you have vectors, these keys and values are just linear transformations of these two vectors. Okay, so we'll get keys and values, and these keys and values are the ones which are used in all encoder decoder attention sublayers. So in the RNN case, we were only having hidden vectors, which were just averaging and so on. Here, the attention encoder decoder attention is slightly different, where we're going to use keys and values generated by the encoder, but we'll use query vectors or query vectors generated by the decoder to somehow get attention weights and averaging. Okay, so values are going to be similar to the hidden vectors that we saw in the RNN case, and keys are going to be keys multiplied with queries generated by the decoder would give us the weights, the alphas or the attention weights that you saw in the RNN case. Okay, so let's say let's say we have passed through the encoder. We got three we got keys and values, and remember we have uh, um, yeah, so we have three words here. So we get three such matrices, and for each of the matrix, for each of the matrix, we can get sorry, 3 such vectors here. Okay, and given the 3 vectors, we can compute a key vector for each word and a key vector for and a value vector for each word. Okay, so here actually the diagram is a little bit has only 2 rows, but you can think of it having 3 rows. We'll talk about the dimension here, but all I'm saying is for each vector here, you just need to create keys, 3 keys and 3 values. Three key vectors and 3 value vectors, and they will be passed to every decoder at every layer. Okay, so let's talk about specifically here. So these keys and values. So let's talk about the operation overall. So these keys and values are used by both the decoder. In this diagram, there are only 2 decoders to generate the first predicted word. Okay, so linear plus softmax is kind of clear what's going on. So these 2 decoders somehow use this key and value vectors, collection of these vectors, to produce the first word. Okay, the first word is then passed on as input to the first position of the decoder block. Remember, a decoder block will again can only accommodate at most some number of words, very similar to the encoder block, right? So once we produce the first output, we're gonna use that output as input. Okay, and this is something that is needed, and this is something that you've seen even with while doing a forward pass in RNN based architectures, encoder decoder architectures. Not while training, but while producing a new text. You produce something, then you pass it on to produce a second thing, then you pass that one on to produce the third thing, and so on. Okay, so that's what you would do. Yeah, and again, you can see that there is this layer, which is the positional encoding, not layer, sorry, the step, which is the positional encoding step that you need to do. And every time you input an embedding for the word into this architecture. Okay. So yeah, this illustration is just showing going from this sequence to this sequence. And eventually, hopefully, you get the end of token sequence as the one with the highest probability, or if you sample, or if you do the beam search decoding that we have discussed before, hopefully you get the end of sentence um, token. Okay. And at this point, you stop decoding. And that's how you do translation within with this transformer architecture. Yeah, and just to wrap up, at every step you are actually passing through a linear layer with a softmax, and this is something that you've already seen. So whenever the last decoder, in this case the second decoder, actually, yeah, there could be 6 decoders or 2 decoders. How many are there? Whatever is the last one, that would have produced an output, right? That would have produced many outputs, right? So whatever is the length of the current length. So for example, if you're looking at 4 words, then we are focused on 4 outputs of the decoder. Okay. At the beginning, for example, when there are only 2 words that have already been computed, we only care about 2 decoder vectors. Okay. Yeah. So you take the decoder output. So you take the last one, and then you do a just linear transformation to get to a vector which is the size of vocabulary, the size of the output vocabulary, the output language, and then you just do a softmax transformation, and you can take the argmax, which corresponds to the highest probability, or you can sample or whatever. So there are many things that we've seen. That's what the output layer looks like, from going from the decoder output to actually a distribution of words and getting a word out. So let me stop here, pause here for a second, and ask if there are any questions.
Professor, I have a question. In the first slide where you were introducing decoder, there were like 2 plus symbols, and on top of that there was 2 layer, which is could you please go
here?
Uh, No. Yeah, here. So there is a self attention and add and normalize.
Oh, these
Uh,
pluses just represent positional encoding. Okay, so just don't worry about the plus sign. It's just, it's just a vector being passed in. Yeah.
oh, okay. So the vectors from encoders are being passed to encoder decoder attention
Yeah.
directly.
So yeah. So the encoded things. So let's say we had thinking machines. At the end of the day, thinking machines. Let's say it's an example sentence. At the end of the day, this whole encoder, collection of encoders produces two words. Okay, a word for thinking. Sorry, a vector for thinking and a vector for machines. Okay,
Okay.
but what you do is don't just use those final two vectors, but from those two vectors you produce two keys and two values. Okay, two keys and two values.
Okay. And what about the query vector?
The query
From
vector
the
is gonna, yeah, the query vector is gonna come from the decoder. So remember, it's so this idea of keys, values, and queries is very similar to the RNN case. In RNN case, remember there was a state of the decoder, and there'll be
yeah,
hidden one, hidden two,
H2.
H3,
Yeah.
H4, I think. So
Yeah.
this H1, H2, H3, H4 is very similar to values. Okay.
Okay.
And
Okay.
in RNN case, S and then at the H1 together would have given you the weight for the first guy. Similarly, S plus S comma H2 would have given you weight for the second guy, and so on, right?
Yeah.
So let me actually output HI. So some function of S comma H2, this is the same function of S comma H1, and so on, right? So these
Yeah.
are the weights. In the transformer case, what you get is there'll be key 1, key 2, that's a key 3, and key 4. So these are keys, and these are values v1, v2, v3, v4. So what we're going to do is we're going to use, so this query is going to serve the purpose of this guy.
State.
Okay.
Okay.
Yeah, it's equal. I wouldn't say it's exactly the same, but in terms of analogy, in terms of understanding attention. So what we're going to do is k1 transpose q, k2 transpose q, k3 transpose q, and k4 transpose q. These are the scores.
Oh, okay. Okay.
Okay. Once we get the scores, we're going to average out with those alpha. Sorry, let me not put alphas here. Um,
Ki transpose.
Scores times vi. Sorry, here it
Okay.
would be sum of scores times
Okay.
hi.
Okay. Okay. Okay.
That would be our attended, vector, and that's what would concatenate with the, the state to again, get the distribution of words. Here, this average thing is the, yeah, this average thing is the output.
Output of
Output of
encoder.
the decoder, encoder
Decoder.
decoder attention, right? Encoder decoder
Decoder.
attention
Decoder. Yeah.
produces one thing per word. So this is the output. Um, yeah, encoder decoder attention is
Okay.
basically, the query is coming from the encoder from the previous, from the previous layer, uh, right? And keys and values are coming from the encoder side to produce. So we're getting something as an input, right? For the encoder decoder attention, we're getting something as input. That's right. From there, we need to produce one vector as the output. So we're getting q as an input essentially, and it's not really q as an input. Some transformation, some whatever is the input, its transformation is q. Okay, and we're getting something as the output.
Okay.
So you can think of q as an
Okay.
input and something as the output. Yeah, this is the output.
Okay.
Yeah, I don't want to
Got it.
complicate it for many of the folks, but yeah, encoder decoder attention is very similar to how we were doing it in RNN case, like
Yeah.
this.
This actually made sense for me. And the other two layer, which is the Professor, could you please go towards the left of the slide? Left.
Yeah, yeah.
So the ones above plus the two layers of self attention and add normalization. What do we give
So
it to that?
here, I mean, for all of them, right?
Hmm.
For all of them, so remember this pink block here is the first decoder. Similarly, this green block here is the first encoder.
Yeah.
Okay, the encoder has, we only focus on attention and feed forward as the two sub blocks inside it. But this extra addition and normalization, extra bells and whistles, or I would say extra bells and whistles, but extra processing that you need to do with the vectors. I just introduced this right after. So we remember the way we discussed this was that, hey, transformer architecture has encoders and decoders. In encoders, there could be several. Let's look at one encoder. In one encoder, there's going to be these blue boxes, feed-forward
Yeah.
networks, feed-forward layer, and this sublayer and the self-attention sublayer. That's what we focus on first. And then we said, hey, it's not just they're passing vectors directly to the next guy. They're actually doing what is called a skip connection. So
Oh,
they're passing the processed vector, but add the input vector as well. So this is very similar to ResNets. Okay. In residual
resonance.
networks
Yeah. Got
also, you do your con transformation, con plus extra few bash norm plus some extra things, and then again you pass the input tensor, add
Yeah.
up both, and then you pass it to the next ResNet block.
Okay.
So it's
Got
very
it.
similar to that.
Okay. Got
Yeah,
it.
normalize is just think of it as very similar to any sort of normalization that you would see. Like there's some parallels to batch normalization, but it's not batch normalization going on here. It's nothing to do with batches. Every training normalization just means, hey, you have a bunch of numbers, take the mean, take the variance, somehow subtract the mean, which is
Mhm.
one number, and divide by the variance. Some scaling stuff. Yeah, that's it.
Okay. Noted. Thank you, Professor.
Any other questions? It's good questions. Actually, I went over some details pretty quickly. Um, but I just want to tell you like what's the mechanism. So encoders just produce vectors, one vector per word, whose transformations, keys, and values are used inside the decoder. Okay. So, and the decoder at any given point of time would have a partial bunch of inputs, as in the partially decoded sentence. Those would be, and those words operations are going to be very similar to how the encoder would have processed, right? Going up. Okay. As in each word again, self-attention, then add normalize and all that. But in between, there is a this self-attention block, not shown here. In between every decoder, there's a self-attention block, which somehow takes external input. Okay, so you could have directly dumped some processing for the partial words, but these external inputs further tell you how to produce the next word. Okay, so it makes sense. I am a student. You want to produce end of the sentence. Given the and keys and values produced from the encoder side, and whatever processing you've done, you may say, hey, at this point there's nothing to attend to. Maybe because of that you get an output vector and whose transformation eventually says highest probability on end of word token, something like that. Okay. Uh, I mean, I was yeah. Okay. So let's pretty much wrap up transformers now and switch over to this new set of topics. So here's the thing, right? So at training, so what we discuss is just one forward pass. Training is very similar in the sense that if these are all layers and you know how to define a forward pass, you would very similar to what you've done in assignment 3 or even in assignment 2. You would call loss dot step and dot backward function, right? To take a gradient step with respect to all the parameters involved. Okay, and the parameters involved are basically those transformations to get keys and keys, values, and queries, and those extra matrices that were there, for example, in the linear layer, and so on. Okay. Um, so let's quickly talk about training. So if you have um, um, words, let's say your vocabulary is only, let's say 6, on the output side, there's only 6 words, uh, sorry, 6 tokens, and they have some indices. Actually, yeah. Okay, so actually the next few slides, I'm just describing binary cross entropy loss. Sorry. Yeah, binary cross entropy loss. So I'm wondering if I should, not binary cross entropy loss, just cross entropy loss. I'm wondering if I should even discuss this because this is probably familiar to everybody. So let me discuss this. So remember at the last layer, we produce a distribution over words, right? Um, a distribution over the output, the output languages words, right? If there are 6 words, I would produce a distribution, like saying that, hey, this word has a higher probability. These are words have lower probability at any given point of time. So let's say I've decoded 2 words. Let's say the third word I want to decode is, let's say, third word I want to produce. There's going to be a probability mass is a softmax value, right? The scores which are transformed to probabilities. Now we know what cross entropy loss function looks like, right? Cross entropy loss function looks like. So you have this vector, and at training time, you actually know what vector should be what word should be the output, what should be the translation, right? So maybe that word is actually I, or maybe the word is something else, student. Um, let's say, for example, I guess in this example, learning example, let's say, uh, yeah. So let's say the true word is thanks, and at a given point of time, you at some iteration, some parameter choices, parameter setting, you're iterating over new and new, different parameters when you do gradient descent, right? So at a given parameter values, you're producing only 0.2, whereas the right word thanks is the right word. So then you want to figure out what should be the change in parameters such that this location, the probability is boosted and increases. Okay, so that's literally cross entropy. So loss function, and you need to do that cross entropy computation across all the positions. So if you have a 5-sentence output, so 5-word output, then you're adding up the cross entropy loss across all the 5 locations. Okay, so for example, in position 1, the true word should be 1. So whatever is the predicted, so you'll have a predicted bunch of probabilities. Hopefully the probability at this location is the highest. That's what you want. That's the parameter such that the probability in this location is the highest. Similarly, for the second word, the probability in this location is the highest, and so on. Yeah, these locations is the highest.
Professor, I have a question.
Yeah.
I'm a bit confused here. So you have a set of words which is a, am, I, thanks, student, and end of sentence.
Yeah,
So
this is
these
just a
are
vocabulary. This is my complete vocabulary, let's say. Yeah, go ahead.
okay. So it's not actually positioned properly, and now we are actually predicting the positions of uh, the words. Is that right?
No, here we are just displaying the one-hot encoding of these words. Let's say these are the one-hot encodings. Okay.
Oh, okay.
What we are saying is that, hey, yeah, we are on the row side. We are actually showing, hey, I should come first. So actually, let's write, I am a student and EOS, right? So that's, yeah, the rows are corresponding to the position of the word that should come in. So here I'm just trying to show, hey, if the first word should be I, then the target for the first cross entropy term will look like the binary, the one hot vector will look like this, right? Where I should be the one which should be 1, everything else should be 0. That's the preferred distribution essentially that you want, right?
Okay.
Yeah, don't get confused with this. This is just a, so if you are producing a file length if you decide at training time, you already know what the translation should be. Let's say it is I am a student, end of sentence. Okay.
Okay.
Which means I know
So
there are supposed
this
to be 5. Yeah.
okay. No, Professor, continue. I'll ask at the end.
I'm just saying that, which means I know that I have to compare what I'm predicting at 5 different locations, right? I could be predicting different things at each of these 5 different locations, as in 5 different words that I'm producing, right? I'm basically producing 5 different distributions of words over the vocabulary, right? Let's
Okay.
focus on position number 1. In position number 1, the target is supposed to have a distribution which looks like this, because in position number 1, I know what the true word should be. It should be I, okay, and I
Yeah.
is third thing in the vocabulary, so it's third location should be 1, and maybe my vector probability vector happens to have higher number at that location. That's great. That means the loss is low. Okay.
Okay. Okay. Yeah.
So
Now.
what we're just seeing is just, hey, 5 positions, 5 ground truth, I guess class ground truth words, the true translation words which are one-hot encoded basically, because we are
Oh.
basically doing a vocab size multi-class classification, right?
Okay. Yes, Professor. Got it.
And 5 positions just means we are doing five multi-class classifications for this one training instance.
Okay. Got it.
Okay,
Thank
because every location we need to do a multi-class classification essentially.
you. Okay.
So that's the targets. These are the predictions. Based on them, you pick the probability here, probability here, probability here, probability here, probability here, and then do a log of the probability and do a negative sign, and then do a minimization. Okay, this is literally probability at correct. location. This is literally cross-entropy loss. This is the definition of cross-entropy loss in a very crude way that I wrote here. It's not incorrect though, so I hope people remember this. Yeah, so minimization of parameters to, and this is what I said, do it over 5 positions. The sum is over 5 positions for one training example. Okay. So that's about it. I just wanted to wrap up transformer architecture. I know I didn't spend too much time on decoders, but as I said, they're almost the same as encoders, so we don't have to go through the explicit computation of how self-addition is happening, how addition and normalization is happening. Only thing that we should have expanded or we should have spent time on is the encoder decoder attention, but that's exactly very similar to the way we saw attention mechanism in sequence or in RNN based encoder decoder architecture. So I didn't spend too much time there. Okay, with that, let's I don't want to spend too much more time on transformers today, or transformer based architectures today. We'll pick this back up when if we can talk about some popular architectures later on once we discuss a fresh set of topics first over the next couple of sessions. So if there are any questions, it's a good time to ask. In the meantime, I'm gonna share my screen. Yeah, sorry about that. So yeah, so first thing I wanted to quickly show is a couple of nice projects that you can download and try. Um, so everybody can see this GitHub page, right? I just lost the chat window. Yeah.
Yes, we can.
Okay. Sorry, I was just trying to paste the link to this. So this is a nice repository, which actually, so we haven't discussed this particular model. It's called GPT-2, okay, the underlying model. It's based on the transformer architecture. It's a little bit different, but based on the transformer architecture. It's doing language modeling, not translation. We have been talking about translation in the whole in this learning example, but here it's doing language modeling. And this is something you've already done translation in assignment 3. So here this repository actually adds a GUI as well and gives you a lot of pre-trained models for doing this translation. Okay, so you can do translation from English to Spanish and back, and they give you a nice way to just get the translate, translation object, and from there a translate function. It's given that, given a sentence as input, produces the translation output. Okay, actually, this is something since you've already done assignment 3, you can actually try it out especially if it may be useful for your projects. Yeah, that's what I wanted to quickly show. A lot of instructions. Let me see. Yeah, I'm trying to see if they explicitly mention which model they're using. I don't see that directly, but yeah, so that's first thing. Second one is this a slightly different sequence problem, which is chatting. I think one of the teams is also working on it. But there's another nice repository called Chatting Transformer. It's based on, again, transformer architecture and they've, again, the underlying, as I said, the underlying model is a transformer-based model. It's called GPT-2. Okay. Of course, this package retrains that architecture, so it's not the model weights provided by the researchers who introduced GPT-2. Okay, so this is some company which I guess proposed GPT-2 some time ago. That's the name of the model, but it's very similar to ResNets and all that. But this repository makes it easy for somebody to download a pre-trained model and like continue a sentence, basically. Okay, this is again a language modeling idea. So for example, here you can see you create an object called GPT-2. It's just a model, and given a text sequence as input, it produces the subsequent text. Okay, so in 10 years AI will is the prompt, and given the prompt, it produces the next few words. I mean, that is based on the model, and there's multiple decoding methods, and this is something that we have also discussed when we're talking about sequence models. You can do greedy decoding, which is take the argmax of the highest probability coordinate as the word. Similarly, you can do beam search decoding, and there are many others. So it may be useful to also explore this repository now that you have also spent a ton of time on NLP in assignment 3. So this is a good choice. Okay, so you can see here they list different types of um, different ways that they can generate text, so that they don't. So if you always pick greedy, you'll always get the same answer. Okay, so instead of that, if you want to get different, I guess, completed sentences, you can try some more stochastic ways of picking and the next word. Okay. So again, let me share this on the chat window, which you can see here. Yeah. So yeah, those two, and let me also quickly mention. I don't know if all of you, tried Google Translate as part of your debugging process. So this is the sentence we were using, and this is the translation, and this is the running example. In addition to thinking machines as the running example in the slide deck, and a couple of more things that I want to quickly show um, is this very recent model called GPT Neo. Okay, so this is a model by a group of researchers who are trying to produce a model similar to this names of the models, which are called GPT-2 and GPT-3, which are based on transformer architecture, as I said. Okay, so they're just trying to reproduce the model weights and create a pre-trained model basically for others to use because the original model is not, I think it's not public at the moment. So yeah, this is something also you can try out. But I guess this one is, I guess, the easiest to try because this already has pre-trained models with a bunch of parameter numbers. Here you can see already that there are transformer models which have 1.5 billion parameters, and in fact the most recent one, GPT-3, GPT-3 and the largest size of that, the largest one among them, GPT-3 has different smaller different, I guess, um, sizes of models. The largest one among them has 175 billion parameters. Okay, that's something that cannot fit in, that cannot definitely fit in the V100 uh, GPU cards that you're getting from Collab, or any of the NVIDIA card that you're getting. Okay, it requires extra engineering work, but I guess these should be feasible. Maybe the smallest one should be feasible. Um, Finally, I also want to show you one final thing about, again, sequence modeling. Here, the problem is called question answering. Okay, so um, these are all NLP tasks. I just wanted to show you one more because it's easy to install a package and try out question answering right now, during the break or after the class. This is using this is by from a package called Transformers, which is maintained by a company here, this company. And inside Transformers, they actually produce many different models. Actually, on the left-hand side, you can see so many transformer-based models primarily. I don't see. Yeah, I mean, there are many models. Let's not worry about it. But you can see here. Sorry, I think I missed. Yeah, you can see here, for example, you create an NLP object from using a um, uh, using this function call, and um, then from NLP object you can actually create. Um, oh, is this? Oh, sorry, the classification. Yeah, sorry. Yeah, create an NLP object, and you say, hey, when creating an NLP object, you say, hey, it's for question answering. And I think the previous example was for sentiment classification, and this is something you also done in assignment 3, I believe, or at least the starter code there was doing sentence classification. Um, so you can see question answering, and then you give a context as in a blurb from which you want to retrieve the answer. Okay, it's actually it's again, this instantiation is already using a pre-trained model. So underneath there is actually a pre-trained model. Given a paragraph, okay, which is the context, you can say, hey, you can ask a question. You can ask a question this way. So given the paragraph, for example, you can ask a question. For example, here, what is extractive question asking? What is it? Okay, and the context hopefully tells you is the task of doing something, and you can actually get answer result. And if you look at the answer key, then you can see the task of extracting an answer from a text given a question. Okay, so we are at a stage where folks have produced, some some of the models definitely are conveniently packaged into appropriate Python packages where you can actually very easily pip install or whatever conda install the package and try out pre-trained models. And I strongly urge folks to try that when you have time or within your projects. If you're using word embeddings, you can um, use embeddings produced by transformer architectures as well. So you can check that in the slide deck as well. So yeah, these are the things I wanted to show. Any questions? So what I want to do is I just showed you some links there. Maybe I should paste the last one as well. Um, it may be useful for folks doing projects related to NLP, having many different type of pre-trained models, or at least benchmarks, right? Um, so what we'll do now is now move on to this next set of topics related to online learning. Okay, it's a slightly different way of thinking about predictions, because deep learning was all about predictions, and not just deep learning, but most of the previous courses that we've seen is all about predictions. But we'll start talking about the business goals, the business objectives, and therefore some relation to predictions and decision making. Okay, and sometimes the relation is not trivial. So we'll see how to bridge that gap and look at very specific problems in decision making, in decision making back to the predictions. So, but before we do that, let's take a short break. Let's resume at in 10 minutes at 7:40. And if you have questions, just uh, paste it on chat or ask me right after the break. Thank you. Just okay. Welcome back, and I'm gonna quickly show one interesting document before we get into the topic of online learning today, or bandits today. So yeah, so the document I was mentioning is this following document, uh, which is actually a paper that was published in a top conference in computer science called HCI, I think, um, or CHI, sorry. Um, the topic, as you can see, is everyone wants to do the models do the model work, not the data work. And so how not working or not cleaning up data or not filtering or accounting for biases, missing entries, and so on, or quality of the data in particular, has a huge impact on the subsequent decisions that you make. Okay, so for example, if you look at the abstract here, they mention prediction problems like cancer detection, wildlife poaching, loan applications. And so, but they are focusing on, hey, data quality is supremely important. And the moment you don't worry too much about data quality, a lot of things suffer. Okay, so it's not just models. You can always keep using more complex prediction models, but the data quality can have a huge impact on decisions. And I guess that's a so that in that sense, I think it's worth looking at this paper. It's called, I think you should search for it. Maybe it has a long title. Um, sorry, that's the name of the title. Sorry, that's the name of the title of the paper. So anyway, let me come back to. So I wanted to show you this because although it's not really related, it's basically saying, hey, don't worry too much about models. Really worry really, I guess, relatively, you should worry more about your data quality. Um, but but the way it's making the case, this paper in particular, is that it's trying to tie predictions to decisions, right? So in, for example, here, cancer detection, wildlife poaching, and loan applications, right? Loan allocations, sorry. So there's decisions involved in cancer detection, like somebody needs to be sent home, or needs to be asked to do additional tests, or needs to you need to perform a operation or surgery on them, or something like that. There are decisions to be made, but they are backed by predictions, right? So um, we're going to talk about decision making quite a bit in this session and the next couple of sessions, and we'll see among various ways you can make decision backed by data, backed by forecasts. We'll look at one particular methodology, and that's actually called sequential decision making. So you make decisions again and again, get some feedback, make another decision, get some feedback, make another decision, but get some feedback. So that's the specific subset that we'll be looking at. Okay, sequential decision making. That's not captured in this discussion, in this paper, for example, but that's what we're going to look at. So let me come back to goals. So what we have done so far is in module 6. So we talked about attention and transformer architectures. We didn't really talk about a specific architecture called BERT. Okay, but we'll look at that and the acronym GPT that we saw earlier right before the break. We'll look at them later on. Okay, after we finish talking about decision making. Okay. Similarly, we'll skip module 7 for now, which is about autoencoders, which is a way to generate new images, very similar to generating new text. If you had a language model, you need to generate new images. You can use variation autoencoders. You can also use something called generative adversarial networks. Okay, and we'll talk about them. But before that, what we'll do is really take a detour into making decisions, because predictions are backed by decisions. Decisions are backed by predictions. So it's a good idea to get a sense of how do you make good decisions. Okay, and in particular, we'll look at sequential decision making. So for today, we're going to look at start with A/B testing as a starting point, and just like what is A/B testing and what is its issues, to jump into the meat for the next 45 minutes or so about what are called multi-armed bandits. Okay, it's just a name for a way to make decisions. It's just I guess a framework to make or it just defines the problem for which there are many solutions. Okay, many solutions to solve this problem, the multi-armed bandit problem. And similarly, there's a related problem called the contextual multi-armed bandit problem. We'll look at those two problems. Okay, these are specific sequential decision-making problems, and there are many, many solutions. We'll look at a couple because it's related to the first, I guess, the second question in assignment 4. Okay, so so that's what we're going to do today. So in general, the goals of this lecture are get a sense of what is sequential decision making, or which is related to what is called online learning, and how is it different than similar to supervised learning. Okay, supervised learning ends at making forecasts, making predictions. Okay, if you are a classifier, it says, hey, this is in class 1, class 2, class 3. But in online learning or in general decision making, you are not talking about classes anymore. You're talking about, hey, decision. I have 10 different decisions that I could take. Like I could go to school tomorrow. I could go to work tomorrow. I could fly to New York tomorrow. Like these are decisions. These are not classes, right? But maybe based on forecasts, which could be classes, or it could be numerical values, like weather, for example, is a forecasted weather for tomorrow may influence your decision, right? Things like that. Anyway, as I said, the goal is to understand what is the multi-armed bandit problem, how is it related to A/B testing, and look at some solutions. And also, if there's time today, we'll talk about contextual bandits. If not, we'll pick it up next session. Any questions in the meantime? Okay, so if not, as I said, I'm not gonna. So I'm just liking this slide to just show that we are not gonna start from the extreme beginning. So the beginning is just motivating decisions and so on. So, and we already saw decisions are important. I guess models are important. Data is important because decisions are important in some high stakes AI applications. But we'll directly start with something about A/B testing, and then directly get into the meat of the session today, okay, which is about multi-armed bandits. So with that, let me share my screen.
Professor, quick
Okay.
question. Have you put any sort of sample code for like the upcoming assignment, like the assignment 4? Because
Yeah,
that
yeah, there is links, right? So for example, question 3, you just need to do sensitivity analysis for a particular algorithm, right?
Mhm.
So the algorithm's code is already there.
Okay.
Okay. I mean, I just switched the screen, so I'm not going to open assignment 3 right now. But maybe, yeah, there is sample code for much of it. I
Okay.
mean, definitely for question 3. Question 1 is just textual question. Okay, there's no code related to question
Mhm.
1. So question 2 is about the algorithms that we're going to discuss now today, and maybe there are links in the slides. If not, if it's not, if there's no links in the, actually you're supposed to code up the algorithms and they're simple enough. But we'll talk about if you want sample code for that as well. Okay, that's related to question 2. Question 3 already has code. Okay. I
Thank
mean,
you.
in fact, you don't need to. So, by the way, folks who got so in terms of difficulty, assignment 3 was the highest difficulty. At least from my perspective, I don't know if it was easy or not. But assignment 4 was actually much easier than assignment 3 for sure. Even assignment 2 is more difficult than assignment 4. Okay, the coming assignment is actually a little bit harder than assignment 1. But the only challenge here is to understand what, the concepts that we can discuss this lecture, this session, next session, and so on. Okay, the ideas are simple, so definitely ask questions. Especially I would suggest look up questions 1 and 2 after the session or after the next session immediately. Don't wait for the assignment deadline because it's basically related to today and next session. Okay, so
Thank you.
yeah, so let me. So I skipped a few slides here, but they were just motivating up to what is A/B testing. So in fact, anyway, this slide already summarizes what is A/B testing. So I wanted to start here. So A/B testing is basically for those who are in the healthcare or medical areas. It's basically randomized control trials. Okay, but randomized control trials, I guess, generalized to any setting. Okay, so A and B just corresponds to two decisions that you want to make, okay, or two choices that you have, and you want to get a sense of which choice is better, and you want to do it in a data-driven way. And if in the internet context, okay, which is I guess the running example here, in the internet context, let's say in an e-commerce website or an app context, you're basically showing your users two solutions, okay, or two variants of your website or two variants of your app. Not the full app, but like let's say it's the same app, let's say a Netflix app, but in one you have the color blue theme, and in another site, another variation, you have the red color theme. Which one is maybe more, I guess, user friendly? Okay, so you just want to know what is the which decision is better, which decision or choice is better, okay, A or B, and the way you and the goal is to figure out if the solution A is better than solution B. Okay, that's it. So here in this picture, you can see that, hey, this is one website, is another website. Is the first website, as in the web pages, design is better than the second design in terms of some call to actions, maybe conversions in terms of sales happening on the website, or whatever it is, information dissemination that's happening on the website, and so on. For example, even the CDC website or things like that, government websites need to carefully think about how to maximize and not confuse users, right? Let's, for example, it's the tax filing season. You don't want to get confused when you visit the IRS website, for example, right? So they, all of these people do, if not A/B testing, some sort of testing with limited group of users to figure out, hey, what is the right way to present information? What is the right way to, or for example, in the case of e-commerce websites, what's the right thing so that people click more or buy more and things like that. But that's on the internet side. But the same idea can be applied to many other areas, as long as the testing is not too expensive. Even if the testing is expensive, people do it, and that's exactly what people do in healthcare, okay, when they test for drugs, okay, for example, or vaccines, for example. Um, so let me quickly discuss the nuances in A/B testing. As I said, A, for example, can mean control. So these are just words used in this framework. And B typically corresponds to treatment. There could be many treatments. Okay, so it's not just A and B. It could be A, B, C, D, E, F also. But let's just talk about A and B, just two choices. A is control, just means whatever is the existing solution, and B corresponds to a new solution or a new model or a new variation that you want to introduce, and you don't know whether the new thing is better than the old one or better than the existing one. Okay, so what you do is you randomly split users. Okay, so the way you do is you have both solutions. You somehow deploy both solutions. Okay, for example, since we're talking about the internet example, let's not use the healthcare example anymore. So an internet example, let's keep both websites. Okay, let's say two variations of the IRS website, and randomly, whenever a user comes and opens irs.gov, they can go to either the first website or the second website with equal probability. Okay, so that's the random split. And once they go to each of the websites, you see how long they stay on the website. Maybe they accomplish their task of maybe filing returns or whatever it is, and see which website is actually aiding them in achieving their goals. Okay? And so then you'll know which solution is better. Okay? And this random split is the key idea here. And yeah, you look at the outcome. So you send these users, let's say you have 100 users, 50 users go to the first website roughly, and 50 users to the second website. And out of each of the 50 users, how many people accomplish their goals, how many people accomplish the goals when they went to the second website. You can collect the stats and then compare, basically do an offline analysis. And that offline analysis is basically a hypothesis test. So basically, we want to do a hypothesis test once we collect these two samples, one sample per variation, or like one set of observations that we got because people went to website A, one set of observations, another set of observations we got because people went to website B. Okay, and it's not just that; it's not need not be website. It would be one set of people got a placebo, other set of people got the actual vaccine. What's the difference, for example, right? So and with a hypothesis test, and these are actually this fall in the category of, I guess, two sample hypothesis tests because there are two samples. And typically the hypothesis is that, hey, the null hypothesis generally is that the two samples are not different. There is no benefit of doing this new thing, the second, I guess, decision or choice, and you want to reject the null. Okay, typically, like if you use the Fisher style testing idea, then you want to reject the null, that they're both the same, that so you can compute p-values and look at significance and all that stuff. Okay, we'll skip that and get to a slightly different issue, which means I'm not going to talk about hypothesis testing because it's not even central to our discussion here. What is important is a slightly different issue with A/B testing. Okay? And that's the issue that we're going to capture or solve using multi-arm bandit idea. Okay, multi-arm bandit problem and the solutions for that problem. Okay? And the problem is that there's of course usual problems like setting the setup experiment in such a way that there is no incorrectness in the data that you're collecting. Okay, so if you don't randomly split users, then you're not able to like, for example, if you split users such that users who definitely will recover using the vaccine do recover, then doesn't mean that the vaccine is effective, right? So there's those issues. But the second issue that we want to address is this point here. Okay, and the third point is just an extension of that. The point is saying, what if we can change who sees what treatment in a dynamic way? So remember, in A/B testing, what we're saying is every time a user comes, the policy, the policy of, hey, this, a user one came, hey, should this guy go to A or B? I just flip a coin, randomly select, right? Flip a coin. If it lands heads, this person sees option A. If it lands tails, this person sees option B. Now the second person comes, but this person, I forget what happened with A. Sorry, I forget what happened with the first user, right? For the second user, again, I'm like, hey, let me flip a coin. If it lands heads, you go to A. If it lands tails, you go to B. But clearly you can see that, and because of this, you actually need to decide a fixed sample size for each variation. Okay? Which means that if you have 100 users, you have to necessarily show 50. I mean, you have to necessarily show 50 users option A, 50 users option B. Okay? Or it's not like you can show less number of times to option B because you're not doing any learning in between, right? So every time a user comes, you're just flipping a coin without remembering what all happened to the previous users. For example, it can happen that in the previous 40 users, they went to A and B, and you know that B happened to be very terrible. Okay, it's a very suboptimal design or a suboptimal option. You already can see that, but that you cannot take that into account while trying to get the new user to go to A or B. Again, you have to flip a coin, which ignores what happened before. Okay, so that is the crucial thing that we're going to fix now with multi-on bandit problem and its solutions, which is that we can change who sees what, okay? who sees what any given point of time. So the 41st user comes in, we can decide whether this person should be shown A or B based on what happened to the previous 40 people. Okay. For example, if the drug is working, okay, if the drug is working, it's not like you want to subject 50 people to no drug and let them die. You would prefer, if you can see that previous 40 people, maybe 39 people, previous 40 people were split equally, let's say, and 20 people did not receive the drug, and 20 people received the drug, and 20 people who received the drug all recovered. Okay, maybe for the 41st person, you want you want to give them the drug. Okay, so that's essentially what is called sequential decision making. You are making a decision based on what happened in the past. Okay, so you're taking feedback from the past. Okay, the past is what happened to the previous 40 people. Okay, so that's basically leads to what I call multi-on-bandit problem. So you want to make your decision dynamically based on what happened before. So every time you make a dynamic decision, in the sense the decision today depends on what happened before, decision tomorrow depends on what all happened before, and decision the day after depends on what all happened before. Okay, so uh, that's the key crux. Oh, okay, and how does this improve? For example, as I said, if option A or option B is better, then more people will be subjected to the better option, okay, and less people will be subjected to the worse option. So that's the informal level idea of where we are going with this. So that was the con with A/B testing, that you have to subject everybody to the same, same number of times, basically have the same number of same sample size per variation. That's I guess the formal term there. Instead of that, here, because you're making dynamic decisions, you can have a higher number of I guess users exposed to the better option. But of course, at the same time, you cannot do the usual hypothesis testing anymore, because this whole data is all messed up. It's not independent or anything like that you can just do hypothesis testing. Okay, so that's the idea. So is that somewhat clear? And the second point here is something that we'll get to towards the end of today's session, or maybe next session, is about how do you make this idea of who sees who sees what treatment, also based on the context. Okay, I said we can make decisions based on what happened in the past. Okay, that's one set of data, what happened in the past. The other type of data that you can have while making a decision now is attributes of that person. For example, if this person is a working professional or this person is a student, here's also information in addition to what all happened to the previous bunch of users, right? While showing option A or option B, for example, right? So you can also make your decision based on the context. And so that adds an extra data. So therefore increases the complexity of the problem a little bit of how to solve the problem. But we'll talk about how to introduce context. But the larger goal, by the way, of me introducing or us looking at both multi-on bandit and then the contextual version of that is to eventually get to what is called a reinforcement learning. And it's an interesting idea. It hasn't had a huge success story like maybe CNNs with ImageNet and all that, but it has some, I would say, decent success stories. Okay, for example, RL-based techniques were used in a Go in a board game playing software, which could beat the world #1 player 5 years ago in 2016 in the game of what's called Go. Okay, Go is the name of the game. And since then, in this case, Google and researchers at Google were able to do that, and since then there's been a lot of advancements. Okay, so RL-based techniques are used uh, in game domains to demonstrate that it works, because in game domains you have an environment, you don't have to work with the real world, and you can show improvements. I think making sequential decisions and show improved decision making. So RL-based agents have tried to play, for example. Multiplayer, the games, strategy games like Dota and so on. Okay. Um, anyway, let's come back to multi-arm bandits, which is the core here. Any questions at this point before I get into the details of multi-arm bandits or the multi-arm bandit problem? Okay, so let me describe the problem first, and then we'll look at a couple of solutions. Actually, 3 solutions. So uh, 4 solutions. But what is the problem? The problem is it's about decision making. So um, you have interactions, you have choices to make at every time period. So it's as if time step 1, you need to make some decision. Time step 2, you need to make some decision. Time step 3, you need to make some decision. And what's the decision? The decision is to pick one of these slot machines. Okay. Slot machines kind of correspond to a decision that you make. So slot machine A, slot machine B, slot machine C. Okay. Any given point of time, you need to make the decision based on what all happened with you trying out these slot machines before. Okay, that's the rough idea. I mean, the slot machines are just figurative. Okay, they are actually trying to represent decision A, B, and C. When you pull an arm of the slot machine, you can see there's an arm to pull. If you pull that arm, what you get is equal to making a choice. Okay, I made a choice to take action A or action B or action C. And if once you make that choice or do pull an arm, what happens is you get back a reward. Okay, reward or feedback. You get rewarded feedback, but that whether you got some money from the slot machine or you did not get some money. So that kind of simulates how for example, the user experience was. Okay, so if the user goes to website A and they spend a ton of time on it, then maybe maybe that means that the content is engaging. Okay, in some sense, right? So that's an example of a reward. So the slot machine is just showing that there's some, you can assume some notion of a probabilistic reward. Okay, so maybe some users spend 10 minutes, some users spend 20 minutes, something like that. And as I said, reward is basically a measure of success. So it could be click, a purchase, or spending a time on the website or something like that. Okay, so the multi-arm just means, since there's one arm per slot machine, the slot machines are called one-armed bandits because they loot your money anyway. Multi-arm bandit problem because there are multiple slot machines. The problem is how to look at the past. You played each of these, let's say A, B, and C slot machines a few times. Can you zero in on the machine which gives you the most money? Okay, you want to maximize reward, and that's the problem. So how do you dynamically take decision? So dynamically pick one of the slot machines based on what all happened with the previous slot machine interactions that you had to figure out the best slot machine, or figure out the best action, okay, or best decision. Okay? So it's exactly, it's similar to what I just mentioned about A/B testing. And you want to look at what happened to the previous people to decide, which, whether the user should be shown option A or option B. Right? That's the same idea. So there are basically capital K decisions or arms or actions, and each will have a known distribution. Let's assume for now there's going to be distribution associated with each of these options or actions or decisions. Okay, let's say the distribution is between 0 and 1. Let's say some sort of beta distribution. So distribution is just I mean, we have seen so many distributions so far. So a distribution between 0 and 1. Okay, for example, uniform distribution is also a distribution between 0 and 1, a continuous distribution. So each time t, the agent picks a decision, like let's call it I subscript t, okay, which is one of the k decisions that you can make, and you get a reward. And the reward you get is tied to the action that you took. If you took action of, let's say, going to school tomorrow, there's some reward that you get. Or if you go to work tomorrow, there's some other reward that you get. And if you travel to New York, you get some other reward, right? So those rewards are all distributed according to the corresponding distribution associated with the action. Okay. And as I said, the objective is to maximize the expected sum of rewards. Expected just because there's a distribution associated with it, so there is some random numbers getting generated. So you want to average it out. Okay, that's the expectation term there. But you want to maximize the sum of rewards, which just means that you need to kind of zero in on the right slot machine or the right action, which gives you the highest and higher rewards. Okay, that's the whole crux of the problem. You want to make sequential decisions. You want to look at what happened before while taking the decision now, instead of doing it in the A/B testing way, where you just flip a coin. If you have 3 options, you flip a coin, 3-sided coin, let's say, and try option 1 with 33% probability, option B with 33% probability, option C with 33% probability. That's not good because that's not going to maximize the sum of rewards. Right? But here we want to care about trying to take sequentially, like improve based on the feedback that we get to figure out which decision is better and better, and so we do better and better. Okay. As measured by the sum of rewards. So the mean of each arm is just the average, is the average of the mean of the distribution for each of the arms. And the best arm is the arm which is the highest mean reward. Okay. So what is missing here is that we don't know a priori which option is the best. That's exactly captured by, you have k arms. If I tell you already that one of these arms has the highest mean reward, has the highest let's say click rate or something, this website has the highest click rate, or this website has the most informative, useful for the users, then you don't even need to do A/B testing, or you don't need to do solve the bandit problem. The whole point is that you have these options, you don't know a priori which one is good or which one is not good. So you have to show these 3 websites, for example, to users in a sequential way, and based on what the users are experiencing, you kind of show the better website more and more, hopefully. Okay, and that's how you would maximize your sum of rewards. Okay, so and that's captured by this notion of what is called a regret. A regret is nothing but, if I know the best option, let's say option C is the best option, like all 3 slot machines or 3 websites, I show the same option every interaction. Let's say there are little n number of interactions. Okay, some, let's say 1,000 customers, 1,000 interactions. So 1,000 times the mean reward I can get for that by showing only option 3 is n times mu star, right? Remember, mu star is the value of the highest mean reward, so it has to correspond to option 3, which we agree that is, let's say, it's the highest, it's the best performing action. Okay, so that's the best you can do. Minus, what did you do in each round? Okay, in each round you picked some arm. It might not have been the best one, but it would have still gotten you some mean reward. So it might have gotten you some reward, right? So you add all those rewards up. Okay, these rewards, if you had chosen always the option 3, then this sum in expectation would be the same as n times mu star. But since you sometimes might have chosen some suboptimal arms, this sum in expectation would be probably somewhat less. Okay, and you want to minimize this difference. If you take the expectation of this guy, okay, and so therefore the expectation of this guy, you want to have this number as close to 0 as possible. That's the objective. And this number is growing with the number of interactions. So 1,000 interactions, 10,000 interactions, whatever. This number, you don't want to grow too much as n grows. Okay, as n becomes 1,000, 10,000, 100,000, or whatever, you don't want this number to kind of keep growing. Okay, as long as the number is growing slowly, like less than linearly, which just means that it's which is something like, for example, a log function is not growing linearly. Okay, linearly means like this, and super linearly means something like this. As long as it's growing less than linearly, it's good, which means that there's some learning going on, in the sense that we are able to make decisions intelligently based on what we saw before. Okay? That's what, in that sense, we mean learning here. Okay? That's what we, in the sense, we mean making good sequential decisions, okay, based on history. Yeah, and here are some strategies, right? So you can always pick the same slot machine and not try out anything else. That will definitely be poor, because you may pick a suboptimal decision and keep going with it. So you'll lose a lot of, I guess, money or rewards. Or you can do a round robin. You try first one, and then you try the second option, you try the third option, you try the first option, and second option, third option, again and again. That's like A/B testing, because you're really not zeroing in or trying to rely on the fact that what happened before. You're not reusing that information, in the strategy or in the strategy. So they are generally not going to be good. Is the problem clear and the objective clear? If there are questions, let me know. Okay. So let's talk about this. And so what we'll do in the next few minutes is just talk about algorithms informally. And the algorithms are not complicated at all. If you really write it in Python, it's just, each algorithm is going to be less than 10 lines at most. And you don't need any packages typically. Maybe NumPy if you want to really use something in NumPy, but you don't need even that. So here's the first algorithm. Okay, it's a very simple algorithm. It's just saying, at each time I need to somehow take into account what I did before, right? Let's say these 40 users did, I showed them different options, and they all fared, they all clicked or not clicked, or they all bought something or not bought something like that, right? I have that information. Now I need to make a decision. What I'll do is, with some probability, I'll pick a random action. Okay, with some probability, fixed number, okay, some parametric number. Say with 30% probability, I'll pick one of these three options, A, B, and C. I don't care. I'm not going to look at the past data. And then with another set of probability. Okay. For example, this epsilon by k. Let's say the k is equal to 3, and epsilon is 9%. Okay. Which means that I'm going to pick with 3% probability a random arm. Okay. With 3% probability, pick arm A. With 3% probability, I'll pick decision B, and with 3% probability, I'll pick option 3. And then with 91% probability, I'm going to pick the best arm. Okay. How do I know the best arm now? I can know the best arm now because I can look at the data now, this time, okay, under this choice. And this choice, what I'm going to do is look at historical data, which is like the, let's say the previous 40 users. They saw option A, option B, option C. Which option seemed to be the best for these users? Okay. Uh, maybe option A, there were 5 purchases. Option B, there were 2 purchases. Option 1, there was 1 purchase, let's say. Then option A seems to be the best. Okay, so I'm going to play the best option 91% of the time. With so this relies on his previous data. And that's why this is taking feedback into account while making decisions, right? And with some probability, I'll just pick a random action. Okay, this is called the epsilon greedy algorithm. Okay. So you can think of the strategy as random exploration is like something like a scientist. They're just doing more risky stuff, and non-random exploration, which is like trying the previously best thing, is like a businessman. They're trying to exploit the situation. That, hey, we know this information. Let's maximize our money or return. Okay, something like that. So this is called, I guess, the word is as I just mentioned, exploit and explore. And epsilon greedy, as the name suggests, has a parameter epsilon, which controls how much you explore and how much you exploit. Okay, and this algorithm, I'll skip the slide. This algorithm, yeah, this algorithm tends to perform well. Okay, there's some theoretical results related to this algorithm. Actually, for our discussion, we will not go into that. But this algorithm, it turns out, it is able to narrow down and make good choices as more and more interactions happen. Okay, and that you can see in this plot here. Let's say we had 5 Bernoulli arms, which just means that we have 5 decisions. Bernoulli arms just means that, hey, for each decision, there's a Bernoulli random variable. Bernoulli random variable is like a coin toss. Okay, they're either 1 or 0. Okay, so there are 5 decisions. Let's say the probability with which you can get ahead, which is like a positive reward, is 0.1, 0.1, 0.1, 0.1, and 0.9. So arm 1, 0.1, arm 2, 0.1, and arm 9, 0.9. So arm 5 has the highest probability of getting a reward. So mean of Bernoulli random variable is the bias is the parameter itself, right? So 0.9. So if I knew these numbers before, I would just pick the last action all the time, because with 90% chance the person is going to buy, or the person likes this 5th option. Okay, user, right? But I don't know that beforehand. So I'll have to apply an algorithm like epsilon greedy. And if I apply epsilon greedy, what happens is, depending on the value of epsilon, this plot is showing how quickly will you pick up the best arm. How quickly will you start choosing the best arm? The best arm is the 5th arm. So you can see that in the first few interactions, they're still, I'm picking the best arm, with 50% chance, with 40% chance, and finally I can pick the best arm with almost, let's say 80% chance here, or something like 75% chance here. And why is this chances differing? Because of the epsilon parameter. Okay, so it's just saying how quickly will you pick up the right choice, and therefore get more and more rewards. Okay, the more with higher probability you pick the right option, the lesser probability you're picking the suboptimal options, and therefore you are able to zero in on the roughly the action or the decision which gives you the best reward. Okay, so that's epsilon greedy. So any questions here? Okay, if not, what we'll do is we'll see 2 other algorithms. One is called UCB, and the next one is called Thompson sampling. Okay, so let's try to look at these 2 algorithms today. Actually, maybe at least UCB today, and we'll see if we can cover Thompson sampling today. But these algorithms, I call them algorithms, but again, they're just ways to look at historical data and somehow decide which of the, let's say, the 3 options to pick now. Okay, so that's all of these are doing. And it's better than just flipping a coin and picking one of the options and collecting data and then deciding which one is the best thing to do. Okay. So let's look at UCB algorithm or the UCB strategy. Okay. Again, we are being a little bit informal here. If you actually look at the papers that define this algorithm, there are variations and all that. But let's just look at, I guess the formal name for the specific one that we're looking at is called UCB1. Okay, and let's look at the algorithm. The algorithm is actually a deterministic algorithm. Okay, so in epsilon greedy, you have to flip a coin with some bias epsilon to figure out whether you're going to be a scientist or a businessman, right? So here, this algorithm doesn't flip a coin, but so in that sense, it's a little bit different. So what does this algorithm do? It does the following. So for each, so let me introduce a term here, which is called B. Okay, the term B. Okay, it has 2 indices, T, S, and 2 subscripts, T and S, and then a input K. Okay, so K is just corresponds to the arm. Okay, so if K is option A, B, and C, or arm 1, 2, and 3. Okay, let's say K corresponds to arm, which means that each arm I'm going to maintain. So this B object is just a number. I need to maintain a number for each arm at any given point of time, and I'm going to maintain this number at any given point of time. This number, of course, I'm going to make it dependent on what all happened before. Okay, and therefore, since there are 3 numbers at any given point of time, if you ask me to play one of the arms or one of the actions, I'm going to play that action which has the highest number, where this number is the highest. Okay, so that's exactly what's captured here. Which arm I'm going to play? Take the argmax, which is index of the location wherever the number is the highest. Okay, so the argmax you must have seen before. Okay, so now all I have to tell you is how is this number computed at any given point of time, given what all have happened in the past. Okay, what all has happened in the past. What all happened in the past is just the people interacting with different options and maybe getting a reward, maybe not getting a reward. That's exactly what has happened in the past, right? So this number B is computed by just computing the average reward that I got for each of the so let's say I'm looking at computing B for, let's say, option 1. the first option, or option A. What I do is look at the history and say, hey, how many times did people see option A? Okay, maybe 10 times. Out of the 10 times, how many times did they buy the product? Okay, maybe 3 times. Then that's the empirical average that you know how successful option A is, just 3 by 10, right? So it's just the running average. Okay, you write that. So this letter S just corresponds to how many times did you show um, option A, or option A. Okay, S is just how many times did you show option A. T is just the current time index. Hey, we have like let's say the 40 users, and then 41st user is what I'm trying to figure out what to show. So T, anyway, you can ignore it. It's just the current time. So the first term is just the average performance in the past. Okay, and this number was also needed for the epsilon greedy algorithm. Epsilon greedy also needs what is the average performance of each option in the past, and just pick the best one with some 1 minus epsilon probability, right? Now there's one more term which is called the bonus term, which is again a fixed function. It's just saying if you play, so it's a some functional form like square root 2 log t by s, where t and s are like the time indices, as I said. So s is the number of times you have played this option. Okay, the less number of times you have played this option, the higher this term is going to be. Okay, and the higher number of times you play this option, because s can only go up to t, right? The smaller this number is going to be. So it's a number which says, hey, if you have not tried an option, the second time is going to be large, okay, which makes you sometimes pick this thing that you did not play enough number of times. Okay? And if you played one of the options too many times, that means you kind of know how good that performance, how good that option is. Okay, so in that case, this term is not gonna, it's gonna be small. So the only thing that affects is, hey, if the mean reward for that choice, because you played it many times, is pretty good, might as well just use that. Okay, so in that sense, this strategy is trying to balance exploitation, just like epsilon greedy. Okay? In epsilon greedy, it was flipping a coin and saying, with some epsilon probability, I'm going to take a risk and try some other action. Here, it's going to it's going to try some other action if that action has not been tried too many times in the past. Okay? Because if you have not tried something too many times in the past, that means you don't have a good estimate of how good that option is. Okay? So that's the way in which this algorithm indirectly tries to manage exploration versus exploitation, or being a scientist versus a businessman. Okay. Um, so that's all I'm going to say about that, except a figure, a figure which shows this performance. Let's say there are 10 actions, okay, 10 decisions, and there are almost a million interactions. So this is really, in a web setting, it won't make sense for, let's say, a clinical trial, right? So almost a million interactions. And what we're plotting here is interaction number. So almost a million interactions. And here we're actually plotting this regret, okay, expected regret. And we're just seeing, as I said, expected regret should be as cumulative regret. It's called cumulative regret. It's just remember, it's n times mu star minus whatever actions that you took over the interactions, and expectation with respect to that. Okay, so this number hopefully is not exploding. Okay, exploding would be something like this, going linearly. If it's a million, something scaling with million. Okay. Instead of that, if the number is going down, that means you're actually making good decisions. You're actually zeroing in on the right arm, okay, more and more. So that's exhibited by this algorithm. Okay, so that's UCB algorithm in I guess a very informal explanation of that. So yeah, so this plot is basically plotting cumulative regret versus time, okay, a number of interactions. So any questions at this point? Okay, I have a couple of minutes. So I'm going to just motivate the Thompson sampling algorithm, and we're gonna recap this again early next session. We're going to also talk about the contextual setting, and that sets the ground for reinforcement learning in general. The Thompson sampling algorithm, again, as I said, we need to look at the past somehow, and based on that, make a decision today and tomorrow and so on, right? So the Thompson sampling algorithm is based on a Bayesian view of the world. Okay, Bayesian view of the world just means everything is a random variable, and I'll just maintain beliefs on these beliefs on, uh, for example, the reward uh, distribution itself. Okay, so for example, um, what I'll do is, remember we had a distribution mu for each of the three options, mu1, mu2, and mu3. Each one could have a parameter, which is the mean of the distribution, right? Mu1, mu2, and mu3. These are the means, which are fixed numbers. In the Bayesian point of view, I'll just maintain a belief. Oh, I don't know what the mean is. Maybe I'll assume the mean is between 0 and 1. So I'm going to assume a beta distribution on the mean itself. Okay. And similarly, I'll assume a distribution on the mean parameter. I'll similarly assume a distribution on the mean parameter. These are all beta, by the way, if you want to keep it between 0 and 1. So so once you maintain beliefs, okay, on the means uh, of the rewards of each of the arms, then what you do is, every time you get a new observation, you update the belief. You do a posterior is equal to prior times likelihood. Okay. Um, So you basically do a base update of these beliefs. Okay, so you maintain beliefs. So as you can see in this algorithm description, you assume a prior, it's just a belief on the parameters. The parameters, the means of the rewards, means of the reward distribution for each of the arm. Okay, so the parameters anyway belong to 0, 1. That's why you assume them to be beta distributions. And let's say you maintain a prior, then what you do is, at every given time step, you take some decision. Okay, and the decision led to some outcome. Maybe they bought the product, or they did not buy a product, or they spent a lot of time on the website or not. Okay. Based on that, you update, you go from priors to posteriors. Okay, you go to a posterior distribution over these parameters. Okay, and that's just Bayes rule. Don't worry how the Bayes rule is applied, because Bayes rule depends on what is the, like, if it's a beta distribution and the likelihood happens to be Bernoulli, then the Bayes rule is easy to compute. Sometimes it's not easy to compute, but that's all fine. So you compute posterior distribution, okay, over the beliefs. Now, how do you take decisions at any given point of time? What you have is these posterior distributions. Okay? Now, how do you make decisions? Is that you sample. So there's one such distribution per action, per decision. You sample a parameter, or a sample a value from each of these, let's say 3 distributions, because you have 3 actions. Then once you get the 3 samples, you take the action which corresponds to the highest sample value. Okay, at this step, it's very similar to the UCB decision-making process. At the end of the day, what I'm trying to say is that you maintain posterior distributions on the mean parameters. From these posterior distributions, you sample three numbers. Okay, 3 numbers because there are 3 decisions to make. So one sample from each posterior distribution. There are 3 posterior distributions. Therefore, I get 3 samples, and therefore 3 numbers, and pick the action which corresponds to the highest number. Okay. Again, it can be reasoned why this controls exploration exploitation, very similar to epsilon greedy as well as UCB. We'll talk about why that is the case next time, but at least the algorithm is simple, right? You can actually write a simple for loop or simple function to do this decision-making process. Given the history, you keep updating beliefs. So these are posteriors. At every time step, you have new and new posteriors. Given the posteriors, you sample from each one of them and pick the index which has the highest sample value. Okay, so that's Townsend sampling. So with that, let me stop. I already exceeded a couple of minutes. So if you have questions, stay back and ask. If not, have a great rest of the week. So let me pause my recording now.